Okay, thank you so much. Good afternoon. I am Shahsavani, and my thesis title is Modeling Emission Analysis of Low Work Function Tethers, supervised by Gonzalo Sanchez Arias. Okay. I'm going to start with the motivation of the thesis and gaps and goals, and then I will continue with the methodology and results we have carried out during the third year of this thesis, and then the remaining tasks to do will be listed, and finally I will summarize the list of achievements we have obtained so far. This work is funded by ETPAC project, which is will end soon in November. Electrodynamic tethers. Thanks to three ingredients that we have in a space: orbital velocity, magnetic field, and ambient plasma, and also exchanging electron between the tethers and the ionospheric plasma, the tether is able to generate Lorentz force. EDTs are innovative and promising technologies, and they have some advantages, like being propellantless and reversible. They are able to operate as power generators in passive mode, and if we assign an onboard power, they can also operate as thrusters. So they have some applications like in deorbiting, reboosting, or station keeping missions. In this thesis, we deal with both bare electrodynamic tethers and lower function tethers. In both cases, the anodic segment is a bare conductive tether which collects electron from the ambient plasma passively. In the case of bare electrodynamic tether, the cathode is an active electron emitter, and in the case of lower function tethers, the cathode is the tether itself, which is partially coated with the lower function materials, and it is able to emit electron to ambient plasma by thermionic and photoemission effect. In lower function tethers, or LWTs, each cross-section of the tether from anodic part to the cathodic part is can be considered as a long mirror or emissive probe. So the current distribution along the tether can be seen as a current voltage characteristic of the emissive probe. So one of the most important things is that we have accurate model for the current voltage characteristics of the low work function tethers. For cylindrical emissive probes, these IV characteristics could be computed by orbital motion theory developed in 2017, but with a very high computational cost, so it couldn't be integrated in a flight simulator. Regarding this item, the goals of my thesis were, first of all, improvement of the loss of Poisson solver to hasten the code, and the second, construction of a broad database of current voltage characteristics for cylindrical emissive probes, and also providing semi-analytical model of IV profiles along the tether. These goals were achieved in the first 2 years of this work, and besides, we need to design a scheme to provide optimal values of design parameters for EDTs for different in different applications, in different missions. And this was the goal for the third year of this thesis. So we proposed an optimal design algorithm for bare electrodynamic tethers equipped with electron emitter, and considering some mission requirements and some figures of merit. It covers both active mode and passive mode. In active mode, we also have onboard power. So we have 4 design parameters: tether length, tether width, the insulated fraction, because a part of the tether is insulated to enhance the efficiency, and we have onboard power. In the passive mode, it's more simpler. We deal with tether length and tether width. We also consider some constant parameters together with average values of ambient variables. So I'm going to go to Reboost scenarios. In Reboost scenarios, our algorithm receives some inputs like satellite mass, inclination and altitude of the orbit, the final initial and final altitude, and also the reboost time. And the cut probability should be less than the threshold. This is a mission requirement. And figures of merit of this algorithm is the mass ratio of the tether system to the satellite, or reboost time. And the outputs are design parameters. So we start with the equation of motion, and we consider the Lorentz force and the drag force, and we can get the evolution of the altitude of the satellite. And because the initial and the final altitude are known, so we can make an integration and find the reboost time as a function of design parameters. And once the reboost time is found, we can compute the cut probability by small debris impact. And for reboost scenarios, we investigated 2 options, 2 conditions. First, non-autonomous. When the satellite company says, I will give you these amounts of power, and you have to live with it. And the second case, when the system is fully autonomous, so the power is also a design parameter. In the first case, when the power is given, for a certain value of tether width, we can compute the reboost time in a plane of tether length and the insulated fraction, and these ISO lines are reboost time, and we can find the optimal values of tether length and insulated fraction for both figures of merit. For the case of minimum mass, we are looking for the minimum length that at the same time satisfy the requirement on reboost. So the things that we need is a tangent line to the ISO line of the reboost time that is given by the mission requirement. And in the second case, with minimizing the reboost time, we have to look for the minimum value of the reboost time and find the corresponding tether length and insulated fraction. In the second step, we should vary the width to see that how the design parameters will change. So we did it, and we compute some performance indexes like the tether mass, and it shows that by decreasing the tether width, the tether mass will decrease, but on the other hand, the cut probability will increase, so it puts a limit for us. We cannot just take lower value for width, because the cut probability goes up. So we have to satisfy the requirement on cut probability which actually we can find the optimum value of the tether width. In fact, we have to solve the three equations together to find the three unknowns of the problem. In the case of fully autonomous system where the power is unknown, is a design parameter, so we solve those three equations for different values of power, and we find the design parameters and performance indexes as a function of power. So for the minimum mass, it shows that there is an optimum point where the mass ratio of the system to the satellite mass exhibits a minimum, but in the case of minimum reboost time, there isn't any optimum point, because you should make a trade-off between the weight, the mass, and the time. For shorter time, you need heavier system. For station keeping scenarios, the inputs of the algorithm is mass of the satellite, the inclination and altitude of the orbit, the mission duration, and again, the cut probability should be less than a threshold, and the condition, the requirement is to keep the altitude at a certain value. And the figure of merit is the mass ratio, and the outputs are design parameters. In this case, since the mission duration is known, the cut probability actually gives us the relation between width and the length of the tether, so we reduce one parameter. On the other hand, the station keeping condition gives us, we can find a function that by solving this function, we can find the required power as a function of tether width and insulated fraction. But by solving this equation, this function, there are three possibilities. We don't find any solution, so we cannot keep the satellite in that altitude, or we may find only one solution or two solutions. Our parametric domain is limited to the case that we find some solutions. Then we can compute the mass of the mass ratio as a function of tether length and insulated fraction, and we can plot it in this plane, and it shows again a minimum that minimize the mass ratio, and we can find the optimal values of tether length and insulated fraction. So in station keeping, we have four unknowns and we have four equations that we solve simultaneously, and we find the design parameters. We repeated this analysis for different values of inclination and altitude, and we found this map of the design parameters and performance indexes for a specific value of the satellite mass, mission duration, and cut probability. The future work plan would be submitting this article on tether design and extending this algorithm to low work function tethers, which is not very difficult because it only adds one more parameters corresponding to the fraction of the tether length, which is coated with low work function materials. So for instance, we can repeat this analysis for different value of this factor, and we find the optimal. And I also would like to to perform energy flow analysis for two-bar model tethers that I have started recently, and it is in progress. These are the articles and presentations regarding to this work. And we also developed some codes. Last year, we have started collaborating with Professor Marchand from University of Alberta to develop a software to infer the plasma parameters using the database that we have generated and the model that Professor Marchand have, radial basis function. And we got very promising results in first steps. We also collaborating with EP2 group in UC3M to do some experiments on emissive probes. And I also had the opportunity to do a 3-month research visit at the University of Padua, supervised by Professor Lorenzini, and dynamical analysis of 2-bar model of Tethers. And thank you for your attention. If you have any questions.